look at this more. They'll always talk about it being normally distributed, so we don't have to worry about skew or anything like that. What's the probability that a player selected at random will be shorter than 5 feet 9 inches tall? Okay, they tell me that it's a mean of 6'1", so notice the 6'1's in the middle, and a standard deviation of 2 inches, meaning we're going up 2 inches each time to the right, we're going down 2 inches each time to the left. So to find the probability that a player selected is going to be shorter than 5'9", basically I'd go to where the 5'9" line is, which is why it's good to kind of sketch these out, less than, I'd go like this and I'd say, hey, so that'd be 2 standard deviations to the left, and I want everything that's less than that, or they're shorter than that. So I'd come to here and I'd say, okay, there's 2 standard deviations. I want everything to the left of that, so I just add these up. And I'd get 2.5%, and that's what we've got here for the answer as well. So that's all I'm really doing when I'm using the empirical rule. Counting the number of standard deviations and seeing the percentages that go with. But what if we add something to that? What if we tell you there's 240 players in the league, how many are taller than 6'3"? So I start going here, okay, 6'3". 1 standard deviation to the right. So I start thinking a little bit. And again, I'll use this long enough until I get used to it, and then I'll quit using it. But 1 standard deviation to the right, and again, I just add those guys up. 13.5, 2.35, the 0.15, and I'd find out that 16% of the players are taller than 6'3", but that's not the question. How many players are? You take the total number of players, 240, times the percentage of them that are covered within those standard deviations, and that'll tell you how many players there are, approximately. May not be perfect, but it's pretty close to being straight on. So, as we start to ask these a little bit, or work through them, and we'll do these couple of exercises on the front, just to kind of get back into the swing of things. So the number of eggs laid per year by a particular breed of chicken is normally distributed with a mean of 225 and a standard deviation of 10 eggs. About what percent of the chickens will lay between 215 and 235 eggs per year? Now, if you wanted to use a pencil and sketch on your half sheet so you could see what the values are, that's cool. If you wanted to sketch yourself a drawing, you could do that too. What I normally do is I say, okay, if the mean's 225, if that's the middle, standard deviation's 10, 215 is down 10, or down 1 standard deviation from there. 235, if I go back to the mean, and I go 1 standard deviation up, 225 plus 10 would put me at 235. So basically what I'm being asked is, what percentage is between -1 and +1 standard deviation? 68. And that's what I'd put for my answer. And then the part B just kind of, again, comes back and says, okay, now I have a number of chickens. I have 400 of them. How many would lay more than 245 eggs per year? Okay, it means 225. If I add 10, it's 235. I add another 10, it's 245. So I'm at a +2 standard deviations to the right. What percentage of the chickens would fall into that category then? Okay, 2.5. So, if I'm going to use it, though, to figure out how many there are, I'd use 0.025, my 2.5%, times the number of chickens. And that would tell me that I'm going to have approximately 10 superstar chickens that are going to pop out more than 245 eggs per year. Again, statistically speaking. Might not be in actuality. But that's the type of thing that I'm going to be working on with these. Let's see, I'm trying to think. I want to see if there's... Okay, I want to do number 2 and 3, and then there's one on the back I want to talk about with you. All right, so let's see. All right, manufacturing, mean of 18, standard deviation of 2/10. What percent of bolts coming off the line have a diameter greater than 18.4? How many standard deviations is 18.4 from the mean? Plus 2. So what percentage of bolts are going to have that greater diameter? 2.5. Because it's always start at that line and then move to the left or right, depending. Okay, so what percent would be, let's see, between 17.8 and 18.2? Yep. Because 17.8 is one standard deviation below the mean, 18.2 is one above. And we always know when it's between -1 and 1, we're going to be at 68%. And again, the way these can be asked can also pose a challenge at times. Daily surface temperature of a lake at a resort has a mean of 82, a standard deviation of 4.2. If you prefer to swim when the temperature is at least 77.8, what percent of the days does the temperature meet your preference? 77.8. Where does that lie? -1. So at least that means we're going from -1 on off to the right, because any temperature above that we're good with. So what percentage, if you start at -1 and go to the right, are you going to have? Remember, when we're at 0, anything to the right of 0 is going to be 50% of my data. So then we just add that extra 34 to it. Yeah, oh, geez, and I took the sheet with me. That's not good. So to me, it looks like we're going to be right around 84. So we have 50 from 0 on to the right, and then that extra 34 from going one more deviation to the left. And again, if that's not a real comfortable type situation right now, keep using the sheet for the time being. All right, so one more here on the back, because we have an oddball. Number 6. All right, over several years, Bertram conducted a study of how far into parking spaces people tend to park by measuring the distance from the end of a parking space to the front fender of a car parked in the space. He discovered that the distribution of the data closely approximated a normal distribution with a mean of 8.5 inches. Holy cow. He found that about 5% of cars parked more than 11.5 inches away from the end of the parking place. What percentage of cars would you expect parked less than 5.5 inches away from the end of the parking space? They didn't tell us what the standard deviation is. But I'm telling you, you can still figure out what percentage it is without it. 5%. Why 5%? Exactly. They both have the same distance from the mean. They're both 3 inches away. So if one standard, whatever this deviation is, whether it's 1, 2, 3, whatever it happens to be, is 5% away, this one's also going to have to be as well, because they're the same distance from the mean. Nicely done. So that kind of gets us back going with some of the things with standard deviation. But there's actually a way to use this a little more. What if the standard deviation isn't exactly 1 or 2 or 3 away? What if it's something in between? Is there a way to calculate that? Yes, there is. So if we flip over here, there's one more main big concept we're going to cover here, and it's called a z-value or a z-score. And what it does is it allows us to find out partial deviations of things. So, like it says here, z-value, number of standard deviations that a given data value is from the mean. So, they have this funky formula here. You don't have to know all the fancy names for all of the Greek letters working here. But basically, what you're going to do is you're going to take the data piece, or I like to call it the score, just because most of the time we are dealing with scores. So the score minus the mean divided by the standard deviation. You're like, well, wait a minute, we're calculating the standard deviation, but we're using standard deviation. Yes. And it'll give me the score to work with. So for instance, when we look down here at this first one, find the z-score. If my score is 18, my mean is 22, my standard deviation 3.1. Basically, you just plug them into the equation, and the value that you get out, in this case, negative 1.29, means that a score of 18 is approximately a negative 1.29 standard deviations away from the mean. It lets us really lock in on a more specific, well, how far away am I really, instead of just putting me in with a group like somebody would be if we called it just 1 or 2 deviations. So if we do that down here on the practice one, again, we're just going to roll with the formula. If you're going to the calculator, you're like, ooh, wait a minute, it says find x this time. Okay, we'll plug in the other info. So if z is 0.73, we don't know x this time. We do know the mean, and we know the standard deviation. Solve it just like you would any algebra equation. So we're going to go ahead, multiply both sides here by 8.2 to start, so we can get rid of that dreaded fraction. And then I'm just going to leave that for a moment. So 5.986. And then we'll just add the 39 to it. So it's our trip back to Algebra 1 for just a moment. You're like, okay. So indicate the position of x in the distribution. What that means is, and this is a little different because we didn't find the z-score, we were actually given it. So this value is a positive 0.73 standard deviations, because that's what the z-score told me. More than the mean, because it was positive. If it would have been a negative, it would have been less than the mean. But that's what the z-score will always tell me. So even if you're finding something else, if it asks you to find the position, it's the z-score that's going to give me that info and let me calculate that. So now sometimes, like dang, everything's got a sometimes. Sometimes I may not want one specific value. I may want a range of values. Is there a way for me to be able to figure that out? There is. And there's actually a simpler way of doing it using the calculator that we're going to play with here for a minute. Then I'll give you some time to play, and we'll play with some more of the other problems too. So for right now, I am going to go past that last page and come up to 10A here, where we actually get to work with some of our new stuff. The start of the problem looks simple enough. Number of videos uploaded daily to a video sharing site is normally distributed with a mean of 181,099 videos and a standard deviation of 35,644. Find each probability. Ooh. Then use a graphing calculator. Okay, we're not going to worry about sketching. We're going to let the calculator help us figure out the values, though. So here's how this is going to work. So we want to know the probability of having 180,000 to 200,000 videos uploaded this particular day. So first, we want to find these corresponding z values. So we'd still go through, we'd still take the value, we'd still subtract the mean, we'd still divide by the standard deviation and get those values. But here's something that I can do instead of having to play with graphing and changing all these different directions and stuff like that. There's a button, and we're going to talk about it even more specifically down in the next section. If you go second we go. So second and vars here, okay, but we're actually getting into a different section of that. And we're going to use this normal CDF. So if I hit that, here's how we're going to plug in here. And I'll kind of make note over here on mine too, so you can see what's heading up here. What we're going to end up doing is there are 4 values that this wants whenever we're typing these in. And as long as we have all 4 of those values, we can type it in and it's really no big deal. So what we're going to do is we're going to type in our minimum, so the 180,000. Then we're going to use the comma here, so just below sign or just above the 7 if you're looking. We're going to put the maximum in. And once I get that, then I'm going to type in my mean next, so one more comma, and I'll write all this down too. Our mean was 181,099. One last bit of info, you'll never guess what it is. We got to get the standard deviation in. So what we're basically asking the calculator to do is we're giving it parameters, we're giving it a minimum and a maximum, we're letting it know what the mean is, what the standard deviation is, and we want it to tell us how much of the data is going to be in that part. So it's almost like finding a z-score of sorts. So I get this typed in, and what you might notice, and then I'm going to come back up because I'm going to write in how this is working. If I'd have gone to all of this other work of typing in both of those, typing them into y equals, finding the shaded part, you're going to find the exact same percentage to the like 100th or 1000th point here. So what this tells me, this 0.21, is that about 21% of the time that's going to happen. But so we can write this in a form that you can actually use later. So we type in the lower bound first. Get the calculator out of the way here. Our upper bound second. And we'll talk about if you don't have an upper or a lower bound, if you just have one, how that works. Then the mean. And then my standard deviation. And what that'll do is it'll tell me the probability for this range of values. And that's infinite. I can use that for something below, something above, something in between. We're going to do all of those different types here so we can see that. But that's always the way that's going to make this simplest. Because otherwise you have all these individual calculations you have to do, and who wants to do all of those necessarily. So you notice I didn't even have to calculate the z-scores. There was nothing about those in here. I just worked it out myself. So what happens though if I don't have bounds on both sides? What if I'm only told, well, I want to find all the values that are greater than 250,000. How am I going to do it the same way? So, same information is up above, except now we're doing it to above 250,000. So here's how we're going to do it. We're still going to have our normal CDF. Low bound. Now how's this going to work? Well, I have a little tip over here to the left. Since our majority of data values, we said it's such a small portion that's outside of it, is plus or minus 4 standard deviations to the mean. In this case, we're going to use a lower bound, upper bound because it's greater than. Come on, Harty. If I need an upper bound, it's going to be positive 4, since that's the largest standard deviation we calculate to. If we need a lower bound, we'd use negative 4. So here, I'm going to do normal CDF. Here's the one catch though. When you don't have an upper or lower bound, okay, when it's not in between, you do have to use the z-score. So, use the z-score when we're missing a boundary. Because I can't use that 4 because it's not the actual, I'm not looking for 4 videos, I'm looking for that in standard deviations. So here, I'm going to use the 1.93, which I'd get by finding my z-score based on 250,000. So I'm going to use my norm CDF. I'm going to do 1.93 with an upper bound of 4. You're like, wait a minute, you didn't type in the mean and you didn't type in the standard deviation. They're worked into a z-score. So if I use the z-score, I can do that. So again, it's second in this vars key right above tangent, right below your down arrow key here. And remember, it's CDF. 1.93 to 4. And then again, that comes out as a percentage. So that 0.027 would be about 2.7% of my information would be in that area. But that's the kicker on these. If I'm missing an upper or lower bound, I got to use the z-score. But otherwise, I just kind of work it through that way. So I want to knock out this number 4 on the back, and then I think we're good then. Unless you find one that you want us to work through together, which I'd be happy to do. All right. So the last part here, we're going to start one of these from the beginning. So we got the lifespans of a certain tread of tire normally distributed. We've got our mean. We've got our standard deviation. Find the probability. And again, I don't care about sketching curves. I just want to know the probability. So let's see here. So first one, I do have an area to work with. So here again, I can, if I want to, I could jump in right now and punch in the information and get the value out. Or I could find the individual z-scores. It's up to you. So for instance here, if I get this opened up, if I have my minimum, and again, we always got to use that comma in the middle. Can't use periods or anything like that. And my max, okay, got those. If I have both of those in the actual values, then I can use my mean and my standard deviation and let the calculator do all of the heavy lifting, including the z-score values. So here, I'd be looking, and I'll get this written in here, so in case somebody's checking things out later, we can be in good shape. So about 45.7% of my data would be included within that part. However, on the other one, I'm being asked again for a value, x is greater than 35,000. So I'll make one more note up here to try and kind of help out. If I look at this, and again, one option I would have are the values that are down here, but I kind of like this idea we're going to work with a little bit better. But you can try this one out and use that and see which one you think you'd be able to remember better. I'm going to go ahead and figure out my z-score for this. So here I'd have my score minus the mean divided by the standard deviation. And I'd go back through and I'd say, okay, move this over here. And I want to make sure I'm using parentheses for my numerator so I don't get an answer that's going to shock me. So my standard deviation is about 2.39. Positive, so to the right. So when I went to do this, I would get my norm up. But again, this is my lower bound because it's at least 35,000. So I'd do 2.39, and my upward bound would be 4, because once we go beyond that 4 standard deviation, it's out there. So just as a reminder, if it's greater than use a maximum value of positive 4. If x were to come up less than, use a minimum value of negative 4. But again, that's only if I only have half of it. I find that easier to type in, and I haven't even typed it in yet, than dealing with, oh, it's 1 minus or it's not. How do I figure that out? When do I know it's 0? When do I go the other way? I don't like all the ands and ifs and buts of doing it that way. So let's see here. 2.394. Not very much. 2 decimal places over, it'd be like 0.8%. That's not very much. But then again, if you think about it, we're way over 2 standard deviations to the right, so it's not going to be very much of a probability that that's going to happen. So that's how these work. And then there's just some reminders on here with that. So your job at this point, because I'll be honest with you, everything in the packet you are capable of doing now. So try to work through as much as you can with the check your understanding questions that go on to the next page and working through those, because that's going to be part of what the assignment is now. But you're going to have time tomorrow in class to be able to work on some of it if you want to. Keys will be up here, and to be able to work on some final review stuff too. So I'm going to get you some flexibility here these next couple of days so you've got some time and don't get overwhelmed with all of this stuff going into finals week.